Close your eyes for a moment and imagine the vastness of space. Not the space we see in movies, filled with nearby planets and dramatic music, but real space. The kind where the distance between stars is so incomprehensibly large that light itself, traveling at 186,000 miles per second, takes years to cross from one stellar system to another. In this ocean of darkness, punctuated by islands of light we call stars, something is moving. Something that doesn't belong to our solar system. Something that has traveled for potentially millions of years through the frigid void between the stars, and now, for a brief moment in cosmic time, it's passing through our neighborhood. Its name is 3I/ATLAS, and it's causing quite a stir. Before we dive into what makes this object so fascinating, let's take a breath and establish some context. The universe is not new to us, but our ability to study it in detail is remarkably recent. For most of human history, the night sky was a mysterious tapestry of lights that moved in predictable patterns. Our ancestors tracked these patterns, built calendars around them, wove stories to explain them, but they had no idea what they were actually looking at. They couldn't know that those wandering stars we call planets were worlds in their own right, or that comets were dirty snowballs from the outer reaches of our solar system, or that beyond everything we could see with our naked eyes lay billions upon billions of other galaxies, each containing billions of stars. It's only in the last century that we've developed the tools to truly observe the cosmos in detail. Telescopes that can see not just visible light but infrared, ultraviolet, radio waves, X-rays, instruments sensitive enough to detect the faint wobble of a star caused by an orbiting planet light years away. Computers powerful enough to calculate trajectories and compositions and velocities with stunning precision. And with these tools we've made discoveries that have fundamentally reshaped our understanding of our place in the universe. One of those discoveries is that our solar system is not a closed box. It's not isolated. Objects can and do enter from interstellar space, and they can leave again, carrying with them whatever velocity they had when they arrived. These interstellar visitors are incredibly rare from our perspective, though statistically they must be common in the galaxy as a whole. Think about it. When stars form, they're surrounded by disks of material. Some of that material coalesces into planets. Some remains as asteroids and comets. And some gets ejected entirely, flung out into the darkness by gravitational interactions. Over billions of years, the galaxy has been slowly filling up with these orphaned fragments, these wanderers with no home system, drifting through the space between stars. Before 2017, we had never definitively detected one of these interstellar visitors passing through our solar system. We suspected they existed. The math said they should exist, but we'd never actually caught one in the act. Then came Oumuamua, a Hawaiian word meaning scout or messenger. It was spotted as it was already leaving, having made its closest approach to the Sun and heading back out toward interstellar space. Its discovery was revolutionary not just because it was confirmed to be interstellar in origin based on its hyperbolic orbit, but because it was strange, very strange. Oumuamua was tumbling through space in an unusual way. Its brightness varied dramatically as it rotated, suggesting it had a highly elongated shape, perhaps 10 times longer than it was wide. It had no visible tail or coma, no signs of outgassing like a typical comet, yet it was accelerating in a way that couldn't be explained by gravity alone. This non-gravitational acceleration is what really caught people's attention. In comets, we see this all the time. As they approach the Sun and heat up, volatile ices sublimate, turning directly from solid to gas. This gas jets outward, and through Newton's third law, every action having an equal and opposite reaction, these jets push the comet, slightly altering its trajectory. But Oumuamua showed no visible signs of this outgassing, so what was pushing it? Various hypotheses were proposed. Maybe it was outgassing, but the gas was made of something that didn't create a visible coma. Maybe it was covered in a dark crust that hid the activity beneath. Maybe it was made of solid hydrogen that was sublimating invisibly. Or, and this is where things got interesting from a public perspective, maybe it wasn't entirely natural. Maybe it was an artifact, a probe, a light sail pushed by the pressure of starlight. This last hypothesis was proposed seriously by some scientists. most notably by astronomers who specialize in thinking about techno-signatures, signs of technology from other civilizations. It wasn't presented as the most likely explanation, but as a possibility worth considering given the unusual data. The public reaction was predictable. Headlines screamed about alien spacecraft. Social media exploded with speculation. Documentaries were made. Books were written. And in the middle of all this, astronomers were scrambling to gather as much data as possible before Oumuamua disappeared forever into the depths of space. The problem was, by the time we realized how interesting it was already leaving. We didn't have much time. We didn't have many opportunities to point our best instruments at it, and so it left us with more questions than answers, disappearing back into the darkness from which it came. Fast forward to the present, and we have 3I/AT-LAS. The designation tells us it's the third confirmed interstellar object, following Oumuamua and 2I/Borisov, the latter being a much more conventional comet that behaved exactly as we'd expect a comet to behave. It had a coma, a tail, it outgassed, it brightened and faded in predictable ways. It was, in many respects, reassuringly normal. It proved that interstellar comets could be just like our local ones, just visiting from somewhere else. 3I/AT-LAS, however, is bringing back some of that Oumuamua mystery, though in different ways. Let's talk about what we actually know, setting aside speculation and focusing on observations. 3I/AT-LAS is on a hyperbolic trajectory. This is the key piece of evidence that tells us it's interstellar. Objects bound to the Sun, objects that belong to our solar system, travel on elliptical orbits. They might be highly elongated ellipses, like long-period comets that take thousands of years to complete one orbit, but they're still ellipses. They're closed curves. The object will come back eventually. A hyperbolic orbit is different. It's an open curve. The object comes in from infinity, swings around the Sun, and heads back out to infinity. It's passing through. It's a visitor, not a resident. The mathematical certainty of this cannot be overstated. The orbital calculations don't lie. This object came from interstellar space, and it will return to interstellar space. Now, where did it come from? This is harder to answer than you might think. Just because we can calculate its current trajectory doesn't mean we can easily trace it back to its origin. Space is big, and objects move slowly on cosmic timescales. 3I/AT-LAS has likely been traveling for millions of years, possibly tens of millions. During that time, stars move. The galaxy rotates. Gravitational perturbations from passing stars or giant molecular clouds can subtly alter trajectories. Trying to backtrack its path precisely is like trying to trace a single drop of water back to its source after it's flowed down a river for 100 miles. You can make educated guesses about the general region, but pinpointing the exact star system is extraordinarily difficult. What we can say is that it came from somewhere in the general direction of a certain region of the sky, which contains thousands upon thousands of star systems. Any one of them could be its birthplace, or it could have come from a system we can't even see, a brown dwarf or a rogue planet without a star at all. The point is, we're looking at a sample of material that formed in a completely different stellar environment, under different conditions, potentially with a different composition than what we're used to seeing in our own solar neighborhood. This brings us to the anomalies. The word gets thrown around a lot, often without proper context. In science, an anomaly doesn't mean definitely aliens, it means something that doesn't quite fit our current models or expectations. It's a data point that stands out, that requires explanation. And 3I/AT-LAS has several features that qualify as anomalies in this sense. First, there's the brightness variation. When astronomers observe an object like this, one of the key things they measure is its light curve, how its brightness changes over time. For a perfectly spherical object rotating steadily, you'd expect a consistent brightness. For an irregularly shaped object, you'd expect the brightness to vary as different faces present themselves to us, with different amounts of surface area reflecting sunlight. We see this all the time with asteroids. A lumpy, potato-shaped asteroid will brighten and dim as it rotates, and by studying this pattern, we can infer its shape and rotation rate. 3I/AT-LAS shows brightness variations, but they're not regular, they're erratic, unpredictable. Sometimes the brightness spikes unexpectedly, sometimes it drops, the pattern doesn't repeat cleanly. What could cause this? Well, if the object is actively outgassing, if it's behaving like a comet, then jets of material could be erupting from different locations on its surface at different times. If the nucleus is irregularly shaped and covered with patches of ice mixed with darker material, then as it rotates and as different areas heat up in sunlight, you might get unpredictable bursts of activity. Maybe one side has more volatile ice that sublimates easily. Maybe another side is covered in a dark lag deposit, non-volatile material left behind from previous passes through other stellar systems. The rotation itself might be complex, not a simple spin but a tumbling motion, what's called non-principal axis rotation, where the object wobbles as it spins. Then there's the coma and tail structure. When a comet heats up, the gas and dust it releases forms a fuzzy envelope around the nucleus called the coma, and the pressure from sunlight and the solar wind pushes this material back into a tail, or often two tails, one of ionized gas and one of dust particles. These structures are usually somewhat predictable. The gas tail points directly away from the sun, pushed by the solar wind. The dust tail curves slightly, following the comet's orbital path, but 3I/8 airs is showing asymmetries. The coma appears lopsided at times. There are hints of what might be discrete jets pointing in specific directions. The tail structure seems to shift and change more rapidly than models predict. Again, is this impossible to explain naturally? No. If the nucleus is rotating and has active regions, specific vents or fissures where gas is escaping, then you'd expect to see directional jets. As the object rotates, these jets would sweep around like cosmic sprinklers. The gas and dust they release would create structures that from our perspective might look organized, even geometric. The solar wind isn't uniform either. It has its own structure, streams and turbulence, and this can sculpt cometary material into unexpected shapes. High-speed solar wind streams can compress one side of the coma. Magnetic fields can channel ionized particles. The interplay is complex. There's also the question of composition, spectroscopy. The analysis of light broken down into its component wavelengths allows us to identify what molecules and atoms are present in the material being released. Different substances absorb and emit light at characteristic wavelengths, leaving fingerprints in the spectrum. For 3I/8LS, early spectroscopic observations have detected some of the usual suspects we see in comets. There's evidence of water vapor, carbon dioxide, carbon monoxide. These are the volatile ices we expect. But there are also some unexpected features in the spectrum, lines that don't quite match the standard references or abundance ratios that seem off compared to solar system comets. Does this mean it's made of alien technology? Of course not. It means it formed in a different chemical environment. The protoplanetary disk around whatever star birthed this object had its own composition, influenced by the star's metallicity, the presence of nearby supernovae that might have enriched the local interstellar medium with heavy elements, the temperature and pressure conditions in that disk. We shouldn't expect all stellar systems to produce identical building blocks. In fact, one of the most exciting aspects of studying interstellar objects is precisely this: they give us a direct sample of exochemistry, the chemistry of other star systems, without having to send a probe light years away. Let's talk about rotation. Objects in space rotate. That's just a fact of their formation and dynamical history. As material collapses to form a larger body, any slight asymmetry in the distribution of mass or any external torques will cause rotation. Collisions can speed up or slow down rotation, or change its axis. For 3I/8LS, observations suggest it's rotating, and the rotation might be changing over time. This is actually expected if it's actively outgassing. Remember those jets I mentioned, the ones created by sublimating ice. They don't just push on the object translationally, changing its path. They can also exert torques, twisting forces that alter the rotation. If the jets aren't perfectly aligned with the axis of rotation, they'll cause the object to spin up or down or change its tumbling motion. This is called outgassing torque, and it's well documented in solar system comets. In fact, it's one of the ways we can measure how much activity a comet has. By observing how its rotation changes, we can infer the strength and direction of the jets. For an interstellar object that we're only observing for a limited time, catching these changes in rotation is both challenging and incredibly valuable. It tells us the object is active, that it's not just a dead rock but a dynamic body responding to solar heating. Now, I want to address the elephant in the room. The reason there's so much public interest in 3I/Atlas, the reason headlines are calling it anomalous, is because of the lingering questions from Oumuamua, and because, frankly, the idea of detecting alien technology is exciting. It captures the imagination in a way that Comet behaves slightly unusually does not. And look, I understand the appeal. The prospect of finding evidence of another technological civilization, of proving we're not alone in the universe, is profound. It would be one of the most significant discoveries in human history, but we have to be careful. We have to maintain scientific rigor. Extraordinary claims require extraordinary evidence. So what would constitute evidence of artificiality? What would we need to see to seriously entertain the hypothesis that 3I/Atlas is not a natural object? Well, we'd need to see behavior that simply cannot be explained by known natural processes. A controlled trajectory change that isn't just the gentle push of outgassing but a deliberate maneuver. A signal, perhaps. Electromagnetic emissions at specific frequencies that don't occur naturally. A structure, something with clear geometric regularity that couldn't form through natural accretion or erosion. A material composition that's impossible to create without industrial processes. Repeated patterns, light flashes at regular intervals that suggest an artificial beacon. None of these things have been observed. What we're seeing are variations and asymmetries that, while interesting and worthy of study, are all explainable within the framework of natural cometary activity. The burden of proof for an extraordinary claim is high, as it should be. Science operates on falsifiable hypotheses. You propose an explanation, and then you test it. If the data doesn't fit, you modify or discard the explanation. The natural comet hypothesis explains the observations we have. The artificial object hypothesis doesn't add explanatory power unless we find data that the natural hypothesis can't accommodate. That said, and this is important, being skeptical doesn't mean being closed-minded. If genuinely anomalous data emerged, if we observed something that truly couldn't be explained naturally, then the scientific community would take it seriously. The process would be rigorous. Multiple independent teams would verify the observations. Alternative explanations would be exhaustively explored. But if after all that, the evidence pointed toward artificiality, then yes, that conclusion would be considered. Science follows the evidence, wherever it leads, but the evidence has to actually be there, and it has to be strong. Let me paint a picture of what's actually happening as 3I/Atlas approaches the inner solar system. Imagine the object itself, perhaps a few hundred meters across, though we're still refining that estimate. It's been in deep freeze for an unimaginable amount of time, far from any star, its surface temperature hovering just a few degrees above absolute zero. It's a mix of ice and rock, maybe with some organic compounds frozen into a solid mass. Its surface is dark, covered in a layer of non-volatile material, the residue from whatever activity it might have had during its formation, or during a previous passage through whatever stellar system birthed it. As it enters the outer solar system, still beyond the orbit of Jupiter, it starts to warm up. The sun is still just a bright star at this distance, but it's brighter than anything the object has experienced in millions of years. The surface temperature begins to rise. At first, nothing visible happens. The most volatile ices, things like carbon monoxide or nitrogen, might start to sublimate, but these don't create much of a visible coma because they don't drag much dust with them, and they don't fluoresce strongly in sunlight. As it gets closer, inside Jupiter's orbit, the warming intensifies. Now water ice is starting to sublimate in certain areas, places where the dark surface has cracks or where previous sublimation has exposed fresher ice below. Gas begins to escape, forming a faint coma around the nucleus. The object is waking up. It's transforming from a dormant, frozen remnant into an active comet. By the time it crosses Mars's orbit, the activity is obvious. Jets of gas and dust are erupting from multiple locations. The nucleus is rotating, so these jets sweep around, creating complex structures in the coma. The solar wind is stronger here, and it's beginning to push the ionized gas into a tail. Dust particles, liberated from the surface by the escaping gas, are also forming a tail, pushed by the pressure of sunlight itself. Yes, light has pressure. Photons carry momentum, and when they reflect off or are absorbed by dust grains, they transfer that momentum, gently pushing the grains away from the sun. The telescopes are watching. Ground-based observatories are tracking its position, measuring its brightness. Space telescopes are taking spectra, breaking down the light into its component colors to identify what molecules are present. Radio telescopes are listening, though not expecting to hear anything, just being thorough. Adaptive optics systems are trying to resolve details of the nucleus itself, though at these distances, even the best telescopes can barely separate the nucleus from the surrounding coma. What the data shows is variability. Some nights the object is brighter than expected, others, dimmer. The spectral lines shift subtly, suggesting different regions of the nucleus are active at different times, releasing different mixes of gas. The shape of the coma changes, sometimes appearing elongated in one direction, sometimes more symmetric. All of this is consistent with a tumbling, irregularly shaped nucleus with patchy activity. It's messy. Nature at this scale is messy. It doesn't follow simple rules. And here's something crucial to understand. Our models of cometary behavior are based primarily on solar system comets. We've observed hundreds of them, but they all formed from the same protoplanetary disk that formed our planets. They share a common heritage. When we encounter an interstellar object, we're applying models developed for local comets to something that might have formed under quite different conditions. Is it surprising that it doesn't fit perfectly? Not really. It would be more surprising if it fit our models exactly, because that would suggest all stellar systems produce identical comets, which seems unlikely. Think about the diversity we see in exoplanets, planets orbiting other stars. We've found hot Jupiters, gas giants orbiting closer to their stars than Mercury orbits our Sun. We've found super-Earths, rocky planets larger than Earth but smaller than Neptune, a category that doesn't exist in our solar system. We've found planets in wildly eccentric orbits, planets around binary stars, planets that orbit their stars backwards. The universe is more diverse than our single example suggested. Why would comets be any different? This brings us to an important philosophical point about science and anomaly detection. When we say something is anomalous, we're making a statement about our expectations, not necessarily about the object itself. Our expectations are based on our limited sample of observations. If we've only studied comets from one stellar system and then encounter one from another, our expectations might simply be incomplete. The object isn't anomalous in any absolute sense. It's just outside the range of what we've seen before. The solution isn't to invoke extraordinary explanations. It's to expand our understanding to incorporate this new data point. This is exactly what happened with exoplanet science. When the first hot Jupiters were discovered, they were deeply anomalous. They violated theories of planet formation that said gas giants should only form far from their stars where it's cold enough for ice to exist. The theories had to be updated. We had to incorporate planetary migration, the idea that planets can form in one location and then spiral inward or outward due to interactions with the protoplanetary disk or with other planets. The anomalies drove the science forward. They didn't prove that hot Jupiters were artificial or impossible. They proved our theories were incomplete. The same process is happening now with interstellar objects. Each one we observe teaches us something. Oumuamua taught us that interstellar objects can have extreme shapes and puzzling acceleration. 2I/Borisov taught us that some interstellar comets are reassuringly normal. 3I/Atlas is teaching us that there's a middle ground, objects that show cometary activity, but with unexpected quirks. Over time, as we detect more of these visitors, we'll build up a statistical sample. We'll learn what's common and what's rare. We'll refine our models. The anomalies of today will become the understood phenomena of tomorrow. But let's also talk about the limitations of our observations. Detecting and studying interstellar objects is incredibly difficult. They're small, typically just a few hundred meters across at most. They're faint because they don't emit their own light. They only reflect sunlight, or if they're comets, fluoresce as solar ultraviolet light energizes gas molecules. They're fast-moving from our perspective, crossing the inner solar system in a matter of months. By the time we've detected them, confirmed their interstellar nature, and mobilized our best instruments, they're often already leaving. This means we're working with limited data. We get snapshots, not movies. We see the object on certain nights when the weather is good and telescopes are available, but we miss it on other nights. If the object does something interesting on a night when no one is looking, we don't know. We're piecing together a picture from incomplete information, like trying to understand an entire symphony by hearing only a few random measures. The brightness measurements, for example, are subject to uncertainty. The atmosphere distorts the light. Clouds can interfere. The object might be at a low angle above the horizon, where atmospheric extinction is strong. Different telescopes have different sensitivities and might see slightly different things. When we combine data from multiple sources to create a light curve, we're making assumptions about how to normalize and compare these different measurements. Most of the time these assumptions are fine, but they can introduce artifacts that look like real variations. Similarly, spectroscopy requires collecting enough light to spread out into a spectrum with sufficient resolution to see the absorption and emission lines. For a faint object, this means long exposure times, but the object is moving against the background stars, so you need to track it carefully. The longer the exposure, the more you're averaging over time, potentially washing out short-lived features. If there's a brief outburst that lasts only a few minutes, a 1-hour exposure will smooth it out into a subtle bump that might be attributed to noise. The point is, while our instruments are remarkably sophisticated, they're not perfect. There's always noise in the data, always measurement uncertainty. Distinguishing real signals from artifacts requires careful analysis. Sometimes features that initially seem significant turn out to be instrumental effects or processing artifacts. Other times, subtle signals buried in the noise turn out to be real discoveries. This is why independent verification is so important in science. When multiple teams using different instruments see the same thing, confidence grows that it's real. For 3I/ATLS, there are multiple teams observing with multiple telescopes. There's collaboration but also healthy competition. Each team wants to be the one to make a significant discovery, to be the first to spot something truly unusual. This creates a dynamic where observations are scrutinized heavily before being announced. No one wants to publish a spectacular claim that turns out to be wrong. Reputations are built on reliability as much as on groundbreaking discoveries. So when papers start appearing in journals, when astronomers present results at conferences, those results have been checked and rechecked. What's emerging from this process is a picture of 3I/Atlas as a legitimate interstellar comet showing cometary activity, with some characteristics that are unusual but not inexplicable. The scientific community is excited about it not because it might be artificial but because it's an opportunity to study material from another stellar system up close. Every spectral line is a clue about the conditions in that distant protoplanetary disk. Every measurement of the outgassing rate tells us about the porosity and composition of the nucleus. Every observation of how the rotation evolves tells us about the distribution of active regions on the surface. These are the questions that drive the research. Where did this object form? What was the chemical composition of the material in that system? How does it compare to our own system? Did it experience collisions before being ejected? Has it passed through other stellar systems during its long journey? Is there evidence of cosmic ray bombardment on its surface from millions of years of exposure to interstellar radiation? Can we detect organic molecules, the carbon-based compounds that are the building blocks of life as we know it? That last question is particularly intriguing. We know that comets in our solar system contain complex organic molecules. Amino acids, the building blocks of proteins, have been detected in cometary samples returned by spacecraft. Sugars, nuclear bases, all sorts of chemistry relevant to biology. The prevailing theory is that comets might have delivered these prebiotic molecules to early Earth, seeding our planet with the ingredients for life. If interstellar comets also contain these molecules, it suggests that this chemistry is universal, that the building blocks of life are being manufactured naturally in stellar nurseries throughout the galaxy. Imagine if spectroscopy of 3I/Etylas detected amino acids or other complex organics. What would that tell us? It would tell us that the pathway to life, at least the chemical prerequisites, is not unique to our solar system. It would suggest that wherever planets form, they're likely to be showered with these organic compounds. It wouldn't prove that life exists elsewhere, but it would strengthen the argument that the chemical conditions necessary for life are common. Conversely, if 3I/Etylas has a composition drastically different from solar system comets, if it lacks certain molecules we consider fundamental, that would also be fascinating. It would tell us that stellar systems can produce radically different inventories of chemical compounds, that the chemistry of planet formation is more diverse than we thought. Either result advances our understanding. This is why the artificial or natural debate, while attention-grabbing, is actually a distraction from the real science. Whether 3I/Etylas is a natural comet or an alien probe, we should be studying it with every tool we have. The observations we're making now are time-sensitive. This object will never return. Once it leaves the inner solar system and heads back to interstellar space, our opportunity is gone forever. We need to gather as much data as possible while we can. To that end, there have been discussions about potential spacecraft missions. Could we launch a probe to intercept 3I/Etylas, to fly alongside it and study it up close? The challenge is timing and delta VEV, the change in velocity needed. Spacecraft launched from Earth have a certain amount of energy based on their launch vehicle and trajectory. To reach an interstellar object passing through the solar system, you need a trajectory that matches its speed and direction, and these objects are moving fast relative to the Sun. Oumuamua was moving at about 26 kilometers per second relative to the Sun. By the time we'd confirmed its interstellar nature and considered a mission, it was already too far away. Any spacecraft we could have launched would have taken years to catch up, by which time the object would be so distant that communication delays and power limitations would make operations extremely difficult. For 3I/Atlas, if it was detected early enough in its approach, there might be a window for a fast flyby mission. You'd need a powerful launch vehicle, probably multiple gravitational assists from inner planets to build up speed, and even then you might only get a brief encounter. But brief is better than nothing. A spacecraft equipped with high-resolution cameras, spectrometers, a dust analyzer, magnetometers, could gather data that's impossible to obtain from Earth. It could resolve the nucleus directly, see its shape and surface features. It could fly through the coma and analyze the composition of the gas and dust in situ. It could measure the magnetic field, the plasma environment, look for charged particle interactions. These missions are expensive and risky, and they require years of planning and construction. The challenge with interstellar objects is that we often don't detect them with enough advance warning. We need better surveys, more telescopes scanning the sky continuously, capable of detecting faint, fast-moving objects at greater distances. Projects like the Vera Rubin Observatory, which will survey the entire visible sky every few nights once operational, will be game changers. They'll detect interstellar objects earlier, giving us more time to mobilize resources. There are also proposals for standby missions, spacecraft designed specifically to intercept interstellar objects, kept in a ready state so they can be launched on short notice when a good target is identified. These would be relatively small, fast spacecraft, optimized for flyby encounters. The technology exists. What's needed is the funding and institutional will to maintain such a capability. Given the scientific return, the cost might be justified. Every interstellar object is a unique sample from the broader galaxy, and the more we study, the better we understand the diversity of planetary systems. Now, let's circle back to the public perception and the media narratives. Why do stories about potential alien artifacts get so much attention? Part of it is simple human curiosity. We wonder if we're alone. We look up at the stars and ask if anyone is looking back. The possibility of contact with another intelligence is thrilling and terrifying in equal measure. It would answer fundamental questions about our place in the cosmos. But there's also a tendency towards sensationalism. Scientists baffled by mysterious space object gets more clicks than comet shows expected variability. Media outlets know this. And in the age of social media, stories spread based on emotional impact, not necessarily on accuracy. A headline suggesting alien technology will be shared widely, regardless of what the article actually says. People often share based on headlines alone without reading the content. This creates a feedback loop. Sensational headlines generate engagement. Engagement drives ad revenue. So there's a financial incentive to frame stories in the most dramatic way possible. Scientists, meanwhile, are trained to be cautious, to hedge their statements with uncertainties, to present multiple possibilities. When a scientist says, "We can't rule out the possibility that this is artificial, but the natural explanation is far more likely," the headline becomes "Scientists can't rule out alien artifact." The nuance is lost. This is frustrating for scientists because it misrepresents their work. Most of them are not claiming these objects are artificial, they're exploring all possibilities, as good scientists should, but their actual assessment is that natural explanations are sufficient. When the media spins this into alien probe discovered, it creates public expectations that aren't met, leading to disappointment and mistrust when the scientific consensus remains that it's a comet. It also has a darker side. When people lose trust in scientific institutions, when they feel they're being misled or that information is being withheld, they turn to alternative sources. Conspiracy theories thrive in this environment. The idea that the government knows it's aliens but won't tell us gains traction. Never mind that modern astronomy is a global, decentralized field with thousands of independent observers. There's no central authority that could suppress information. If 3I/Atlas was genuinely showing signs of artificiality, amateur astronomers with backyard telescopes would be seeing some of the same things as professionals. Transparency is crucial. When observations are made, they're typically shared with the community quickly, often through telegrams or preprint servers before formal publication. The data is available. Anyone with the expertise can analyze it. This openness is a strength of modern science. It means extraordinary claims can be verified or refuted rapidly. It also means there's no room for cover-ups. The truth, whatever it is, will come out. So where does that leave us with 3I/ATLS? As of the observations we have, it's behaving like a comet. An unusual comet, yes, but within the range of behaviors we might expect from an object formed in a different stellar system and subjected to millions of years of interstellar weathering. The brightness variations are explained by irregular outgassing and rotation. The spectral features are explained by a chemical composition that differs from but isn't incompatible with solar system comets. The coma and tail structures are explained by jet activity and solar wind interactions. Are there still unknowns? Absolutely. Science is about reducing uncertainty, but there's always some uncertainty remaining. We don't know the precise shape of the nucleus. We don't know the exact composition at different depths. We don't know the internal structure, whether it's a solid chunk or a loosely bound rubble pile. We don't know if it's had previous close encounters with other stars that might have altered it. These are questions we'd love to answer, and continued observations will help. But the absence of complete knowledge doesn't justify jumping to extraordinary conclusions. It's like seeing a bird you don't recognize and concluding it must be a dragon. The unknown bird is interesting and worth identifying, but it's almost certainly still a bird, just a species you haven't seen before. 3I/ATLAS is an unknown comet, so to speak. It's interesting and worth studying intensely, but it's almost certainly still a comet. That said, what if it isn't? What if, as observations continue, we find something genuinely inexplicable? What's the protocol? Well, first, the observations would be scrutinized mercilessly. Extraordinary claims face extraordinary skepticism, rightly so. Multiple teams would try to replicate the findings. Alternative explanations would be explored exhaustively. Instrumental errors, data processing mistakes, statistical flukes, all would be ruled out methodically. If, after all that, the anomalous signature persisted, you'd see scientific papers with very careful language proposing that known natural mechanisms cannot explain the observations, and that alternate hypotheses, possibly including artificial origin, warrant consideration. There would be calls for additional observations, perhaps with different types of instruments. Radio telescopes would listen more carefully for any signals. Proposals for spacecraft missions would be fast-tracked. The international community would get involved. Organizations like the International Astronomical Union would coordinate efforts. Protocols for announcing potential techno-signatures developed for SETI would be activated. The discovery would not be announced to the public until there was high confidence, precisely to avoid false alarms. When the announcement came, it would be framed carefully, explaining what was observed, what has been ruled out, and what the implications might be. And then, humanity would have to grapple with the reality of not being alone. The philosophical, theological, and sociological implications would be profound. But we're not at that point. Not with 3I/ATLAS. Not yet. Maybe someday, with this object or another, we'll encounter something that truly defies natural explanation. Until then, we do science. We observe, we measure, we model, we refine our understanding. The beauty of this process is that it's self-correcting. Mistakes get caught. False leads get abandoned. The community converges on the explanations that best fit the data. It's not perfect. Science is done by humans, and humans have biases and blind spots. But the method itself, the insistence on evidence and reproducibility, keeps us moving toward truth. Slowly, sometimes frustratingly slowly, but reliably. For those watching from the outside, for the people who read the headlines and wonder what's really going on, I'd offer this advice: look for the primary sources. Read the actual scientific papers when possible, or at least read articles written by science journalists who specialize in astronomy and who cite their sources. Be skeptical of claims that rely on anonymous sources or that promise revelations without showing data. Trust builds when predictions are tested and confirmed. Astronomy has a good track record here. When astronomers predict an eclipse, it happens. When they calculate an orbit, the object follows it. When they model stellar evolution, observations match. 3I/ATLAS, whatever its ultimate nature, is a gift. It's a messenger from the depths of space, carrying information about places we can never visit. Every photon we collect from it tells a story. The slight Doppler shift of a spectral line tells us the velocity of the gas escaping. The polarization of reflected sunlight tells us about the size and shape of dust grains in the coma. The ratio of different isotopes, if we can measure them, tells us about nucleosynthesis in the star system where this object formed. These are profound insights, not diminished by the object being natural. In some ways, they're more profound. An artificial object would tell us about one civilization's technology at one moment in their history. A natural object tells us about universal processes, the physics and chemistry that govern how matter behaves throughout the galaxy. It connects us to the broader cosmos in a fundamental way. As 3I/Atlas continues its passage, observations will continue. New data will refine our understanding. Papers will be published. Debates will happen at conferences. Graduate students will write theses analyzing aspects of the data. This is the rhythm of science, the methodical accumulation of knowledge. It's not as dramatic as alien contact, but it's real, and it matters. And who knows, maybe years from now, when we've studied dozens of interstellar objects, we'll look back at 3I/ATLAS as the one that taught us something crucial about cometary diversity, or about the chemical inventory of planetary systems around stars different from our Sun. Maybe it will be a footnote in a larger story, or maybe it will be a key data point that shifted our understanding in some fundamental way. That's impossible to know now. We're too close to it, in the middle of the investigation. What we can say is that the universe continues to surprise us. Every time we build a better telescope, develop a more sensitive detector, or invent a new analysis technique, we see things we didn't expect. The cosmos is richer and stranger than any one person can imagine, and that's wonderful. That's what makes science exciting, not the prospect of proving our wildest speculations, but the certainty that reality is waiting to show us things we haven't even thought to speculate about. So breathe easy. 3I/ATLAS is not a threat. It's not a harbinger of invasion or a sign of impending doom. It's a cosmic wanderer, a frozen relic from another star's family passing through our neighborhood and giving us a chance to learn. We should observe it with every tool we have. We should analyze the data rigorously. We should publish our findings and debate their interpretations. And we should remain open to possibilities while insisting on evidence. That's the path forward. Not panic, not unfounded speculation, but curiosity tempered by discipline. The universe is vast and we're only beginning to explore it. Every object like 3I/AT-LAS brings us one step closer to understanding the full diversity of what's out there. And that journey, that gradual illumination of the darkness, is one of humanity's greatest endeavors. So let's watch the sky, collect the data, and see what this visitor has to teach us. The answers, whatever they are, will be worth the wait.